Thanks everybody for thanks everybody for joining us for the first speaker series with the CAAV. Today we've got Dr. Kenny Gruchalla. He's going to be his title of his talk today is Embodied Cognition and Perception: Immersion for Scientific Data Analysis and Knowledge Discovery. Dr. Kenny Gruchalla is a senior scientist and a distinguished member of the research staff at the National Renewable Energy Laboratory, where he leads the visualization team and manages the state-of-the-art visualization laboratory, the Insight Center. Kenny has more than 25 years of professional experience in scientific programming and scientific visualization, spanning several scientific disciplines, including energy, atmospheric science, geophysics, molecular biology, and environmental engineering. His work is primarily focused on developing interactive scientific visualization techniques that provide tools for finding meaning in increasingly large and complex data. He holds a PhD and MS in computer science from the University of Colorado at Boulder and a BS in computer science from New Mexico Tech. Kenny, thanks so much for giving this talk today, and I'll hand it over to you.
Great, let me share my screen. Can you verify that you're seeing that?
Yes, I can see your screen.
Awesome. All right, so as mentioned, I'm a senior scientist at the National Renewable Energy Laboratory. I designed and now manage the Insight Center, which is NREL's state-of-the-art visualization laboratory. And this includes a large immersive virtual environment. So it's kind of one of our flagship capabilities as part of the Insight Center. So today I'm going to talk about some of the successes that we've had using immersion. And this is in fact an updated version of a talk that I gave to the very first CAAV several years ago. So I know, at least I know Winifred was there. I don't know, and there may be others in the audience, but there will be some new information here. Ultimately what an immersive system is trying to do is replicate real world stimuli. And the immersiveness of a system really depends on several factors. And I list a few of those here. The first of which being an egocentric perspective. That is, the scene is being rendered based on the physical position and orientation of the user's head. That is, we're getting that kind of structure from motion depth cue. Kinesthesia support, so that's the awareness and position and the movement of one's own body, right? So that's something that the CAAV does very well. I have a good understanding of my position orientation of, say, my arms in relation to the data. That's something a lot of the VR headsets today do not provide good support for. Field of view, kind of the size of the visual field that can be viewed instantaneously. Again, good support for that in this large scale environment, generally poor support for that in head mounted displays. Resolution, stereopsis, and the ability to interact with 3D objects directly in 3D space. So I do want to detail some of the knowledge discovery successes that we've had, but first I want to contextualize those capabilities with our current understanding of cognition and perception. Fundamentally, like, why do we want to visualize our data? And it's, and I really want to argue it's more than just about communicating our results. It's about better understanding our data. As an example of this, in 1973, F.J. Anscombe developed Anscombe's quartet to demonstrate the value of visualizing your data compared to just using summary statistics. The quartet is 4 data sets, which I show here, and they have identical summary statistics. So they have the same mean, the same variance, same correlation, same linear regression, suggesting that these data sets should be markedly similar. However, visualizing these data sets with a simple 2-dimensional scatter plot, we see that they're markedly different, right? One of these is a linear relationship, others have nonlinear relationships, a couple being skewed by outliers. Now, there are, of course, statistical methods that can tease out these differences, but they require a level of sophistication far exceeding the sophistication of simply plotting these data and looking at them. But really, Anscombe's point here was that without a visual understanding of our data, without a qualitative understanding of our data, it's really hard to understand what statistical or quantitative methods to apply. So we use visualization because we have this very sophisticated pattern matching machine that sits on our shoulders. We're readily able to identify patterns and anomalies in visual data, and we're able to contextualize those patterns with all of our domain knowledge. So let me step through a more complex example with some NREL data. So here, instead of visualizing 11 points, I'm going to visualize 12 million points. So this project is investigating using the thermochemical conversion inside a fluidized bed reactor to gasify biomass stock. Here, we're using computational fluid dynamics to understand and optimize that reactor design, modeling the physics of those 12 million particles as elastic spheres. So what I want to concentrate on is how we visualize those 12 million particles, those 12 million points. Literally an infinite number of different ways that we go about visualizing those data, but we took a very specific tact here, right? The simplest thing we could do is just render each one of those points with a constant color. So in graphics terms, this is emissive lighting. Consider the rendering of the single spherical particle sitting on a plane in the upper right of this slide. Here, for every point on that surface of the sphere, we're just going to calculate the color based as the product of the ambient light in the scene and the sphere's ambient reflection coefficient. So this uniformly illuminates that surface. And when we look at that single particle rendering, we don't really understand what we're looking at. Are we looking at 2D geometry, a circle and a trapezoid, or are we looking at 3D geometry, a sphere and a plane? And what is that relationship? And likewise, when we look at our 12 million particle rendering on the left, there's really no information being conveyed here. Now, more typically, we illuminate these particles with one or more light sources, where the surface intensity of those particles will depend on the direction of the lights, right? So we cast rays from each of the lights to the point on the surface of the sphere, calculating or modulating the intensity of the light as the cosine angle between those rays and the surface normal at that point. If we do that, now we see that single particle rendering, we have a pretty good sense that we're looking at a sphere, but we still don't really understand what that plane is or what our relationship is, or our relationship to it is. Likewise, when we look at those 12 million particles, we begin to see some texture, but we still don't really have any information. We can improve things by adding a shadowing term. So casting a light from every point back up to the lights. And if it reaches the light, then we have illumination. If it hits some geometry, we cancel out that lighting term. Here we get kind of hard shadows. So for the first time, I understand I've got a sphere and a plane. And when I look at my 12 million point rendering, now I'm starting to understand that I have some cavities forming in that sand bed. Now, the way we actually approach this is with ambient occlusion, right? So we want to calculate the occlusion of the local geometry. So we cast rays in every direction from our point on the surface, and rays that reach the sky increase the brightness, while rays that hit some geometry contribute no illumination. When we look at our single particle rendering there, now we've kind of got this really soft scene with these soft shadows. And for the first time, we have a very good understanding that we've got a particle sitting on a plane as opposed to, say, hovering above it. And on our 12 million particle rendering, we're really starting to get a better understanding of kind of the concavity of those bubbles that are forming inside of our sand bed. Now, the point that I'm really trying to make here is, why is that right-hand image so much more successful in terms of our understanding? And I argue it's because we're better capitalizing on that 50% of our brain that's dedicated to visual processing. We're automatically able to process and better understand the complex structures in that second image because it's mimicking the way that light works in the real world. We're subconsciously able to process what all those light and dark areas mean in terms of the structure. Now, this is precognitive. We're not having to sit here and think about what those dark areas mean. We automatically understand what we're looking at. This, of course, is a lighting and shading depth cue that I'm describing. And we use a whole variety of depth cues in our on our day-to-day lives as we navigate the world. It turns out one of the strongest depth cues is structure for motion. So this is, of course, our ability to kind of differentiate the relative position of objects around us, because objects in our near field move faster than the objects in the distance relative to the motion of our heads or our bodies. We often think about depth cues in terms of stereopsis, but there are others. There are more subtle ones, such as convergence and oculomotor accommodation. So that's really about kind of the muscles in our eyes and how those change depending on where we're focusing. So it's giving us some neuromuscular feedback to depth. At any rate, depth cues are what are going to differentiate three-dimensional data from its two-dimensional projection. And as an example, I've got a cloud of 3D points here, but I'm employing no depth cues. So really, we're just looking at that 2D projection of that 3D cloud. And here I would challenge you to look for structure in that cloud. And if you're like most people, you're not going to see that structure. However, if I simply begin rotating this cloud, most people are going to be able to identify some structure. So if you watch, you'll probably be able to see some structure forming there in the center of this cloud. Frustratingly, as soon as I stop rotating it, you're likely to lose that structure, even though that you know exactly where it's sitting. So kind of with that context, let's talk about our immersive environment and the successes that we've seen there. So the very first thing that we ever looked at in our immersive environment was OPV morphologies. So here, what we're doing, this is the active layer of a solar cell. The idea is we've got two materials, a polymer and a fullerene, and they've been annealed together. So that's kind of the red and the blue. A photon comes into this material. There's an excitation, creating an electron and a hole. Those two charges flow down these kind of respective colors. And if they meet the electrode or electrodes, you have charge. And if they meet back up in the middle of this material, then they cancel each other out and you have a less efficient solar cell. The idea here is we're simulating hundreds of thousands of different materials on our high performance computer, trying to understand and measure which of these materials is likely to be the best candidate, and then picking the top 2 or 3 to go synthesize in the laboratory. So we're looking for ways to really measure kind of the structure properties of these materials. So we spent a lot of time looking at visualizations like this. Here we've taken a skeletonization of that material. So effectively looking at the bones of those polymers and fullerenes. And as I mentioned, it was the very first thing that we put up inside the immersive environment. And I invited the PI to come over and take a look. And he was really excited because he said, this is going to be a really great way for me to explain my science to my program manager and others. Well, he put on the track glasses and he took 3 steps into the space. And he said the 3 most exciting words in science. He said, that's funny. For the first time, he appreciated the heterogeneity of these junction pathways. So if you notice kind of over my left shoulder there are kind of 6 pathways all coming into a junction. But then if you follow that blue pathway kind of in front of me, the next junction only has 2 pathways or 3 pathways coming into that junction. So that heterogeneity really speaks to the degrees of freedom that these charges have to kind of move throughout this material. And what this did is it changed the way that the science team was calculating the structure properties on these materials. So we're back to what Ancom said, right? We want to develop a qualitative understanding so we can better develop our quantitative measures, and that's exactly what happened in this case. I have another example from OPV. So again, here we're looking at these OPV polymers, and there were 2 kind of candidate polymers. And they had done some XRD imaging that suggested that both of these polymers were stacking something called pi stacking in a similar way. When we visualize these kind of in 3D, the science team still believed that these 2 polymers were stacking in a similar way. But it wasn't until they walked into the immersive environment that they were able to definitively identify that one of these materials was stacking and then the other was not. So there's something really, really interesting happening here, right? Because if we back up a slide, here, we're employing 2 really successful depth cues, right? We've got like the sophisticated lighting model, as well as this structure for motion by rotating these 2 polymers. And yet, it wasn't until we had this structure for motion that the science team kind of were able to definitively identify what they were looking for. So why would that be? What's going on here? Well, there's this theory of embodied cognition that suggests that our thinking is an inseparable combination of our bodies and our minds. That is, that higher cognitive functions have been empirically tuned phylogenetically and ontogenetically. That is, through the evolution of our species, as well as learned over our lifetimes by our physical perception and our physical interactions with the world. That is to say that our capacity to reason has actually emerged from various sensory motor experiences. And beyond kind of what I'm showing you here, there's a whole variety of evidence out there that supports this theory. So for example, there are several neurophysiological studies inside of fMRI machines that show that higher level reasoning activates area of the brain that are predominantly concerned with motor control. There are behavioral studies, dozens of behavioral studies that suggest that sensory motor knowledge affects both language and numerical processing. So I believe that the reason that we're discovering these structure properties in the immersive environment instead of the desktop visualizations is because we are better leveraging some of that cognitive machinery. Now, if you buy into this notion of embodied cognition, it's easy to take the next logical step to say, oh, we should just simply view everything immersively in 3D. And I think that's clearly a mistake, and let me show you why. So here we're visualizing a policy model that's looking at renewable energy adoption across the United States, such that we're looking at cities and their investments, and those investments are shown as cylinders, the scale of the investment, kind of the size of their volume of the cylinder centered on the city. And here, I think this is a perfect example of why you don't always want to look at things immersively. You don't always want to look at things in 3 dimensions. Because if I were to take these same data and put them onto a 2-dimensional projection, now all of a sudden I can see all the data simultaneously. While in 3 dimensions, a lot of that data was obfuscated or obscured by the data itself, by the representation, right? So I've got those columns, and some of those columns are hidden behind other columns. And even though I have that egocentric perspective that I can walk around and see everything, if I just simply put this in a 2-dimensional projection, I can see all the data simultaneously. Now, this is a perfectly good projection or representation if the question I'm asking is where that adoption is happening. However, if I care about the distribution and the relative sizes of those investments, I'd actually be much better served to simply look at this as a 2-dimensional bar chart, because now I can start making some quantitative assessments about those uptakes. So it really depends on the data and the questions that we're asking of the data. So when should we use immersive visualization? And of course, we don't know. That's still a very open research question. However, after a decade of using immersive visualization at NREL, we've begun to develop some intuition. So here's a hypothetical graph, and I think there are a variety of different dimensions where we can think about kind of the value of immersive visualization. And that first dimension I want to talk about is spatial complexity, right? So I think the value in terms of perception, cognition, discovery are going to be a function of spatial complexity. So as we go from something that's not terribly spatially complex to something that is, if your data isn't very spatially complex, I don't think you're going to see really any benefit to looking at that data inside of our immersive environment, say, versus something that's lower immersion like a desktop. But as that spatial complexity increases, I think you're going to hit some technology inflection points where all of a sudden there is going to be some kind of perceptual cognitive value of looking at that structure immersively. And then I suspect as we go higher, that we might see other inflections. So, I'm hypothesizing here at the end that as the structures get more complex, you might actually see another inversion to where a desktop, overtakes HMD, for example. And I think that gets back to kind of those immersive factors, where I think as you get into really complex structures, having a narrow field of view is going to be detrimental. So, things like HMDs with narrow field of views are really going to be problematic. There are other dimensions that we've seen that I think really tie into kind of the added value of immersion. One of which is interaction, right? So this was a partnership with Ford, where we're looking at zonal cooling strategies. So we're trying to maximize cooling around the driver inside this Ford Focus. So this was a computational and a physical experimental regime, and we looked at these data kind of in a variety of ways. including inside of our immersive environment. But here we're allowing the researchers to kind of physically probe that flow inside of the cabin. So they can drop massless particles in the flow, watch where those particles evect, and the color of those particles change as a function of the temperature. So even though the engineers had spent quite a bit of time looking at other visual representations, it wasn't until they walked in and kind of physically explored this flow that they appreciated several aspects that they hadn't found before, such as some areas of high flow, which they wanted to mitigate, and several vortical structures that they hadn't previously appreciated. So kind of this brings in kind of notions of two more dimensions when we're thinking about the added value of immersive visualization, really in terms of like usability and understanding. So the first would be spatial interactions. So again, if the interactions that you're making are one-dimensional, so sliders, buttons, things that are typically kind of in that realm of graphical user interface, I think you're going to be much better served in a low immersion environment like a desktop. But as those spatial interactions increase to 2D, like selecting points on a surface, or even better, 3D, for example, placing seeds inside of a flow, that's where I begin where somewhere in there, we're going to hit those technology inflection points. Likewise, I think the same is true for visual representation. So, simple 2D plots and charts probably better served on, a desktop. But as we move into more complicated structures, 3D plots and charts maybe somewhere in there, but certainly as we get into kind of structures, isosurfaces, volume renderings, that's where I suspect we're going to see a big benefit. Another area that we've seen a value is in multivariate interactions and understanding kind of complex multivariate interactions. The best example of that I have is of this distribution management system. So you can think of this as kind of the electrical system, running through, a neighborhood. And we were looking at this particular system because there was a large-scale PV generator kind of in this neighborhood that was stressing some of the control equipment. So we're trying to figure out how to better control that system. At any rate, when you think about distribution management, typically you would have a visualization, a geographical visualization, where you're looking at the actual electrical lines kind of running through that neighborhood, as well as a series of time series plots kind of looking at the three-phase power. So there are a whole variety of variables that you might want to look at on that three-phase power. Using our immersive system, we were able to use that extra degree of freedom. And using that extra degree of freedom, we took those electrical lines and we hung them as a function of their voltage. And in doing so, now we can separate those phases. So red, green, and blue representing A, B, and C respectively. So now all of a sudden we can see, really interesting phenomenon like the blue and the green up there, B and C, separating as a function of their topology. In addition to showing you three-phase voltage here, we're also showing you real and reactive power. So on the width of those lines, we're showing you real power. On the height of those lines, we're showing reactive power. So effectively, just using that extra degree of freedom, we now have embedded 11-dimensional space, right? We have 3 phases of real, three phases of reactive, and 3 phases of voltage, all in the 2-dimensional topology. So now we can actually see these really complex multivariate interactions happening. And that's how this was used to augment the workflow. So our power system engineers run a new control setting or run a new day, and then they would look at that series of time series plots and these 2D plots. And if they understood what they were looking at, they were happy, and I did not hear from them. But occasionally they'd run a new scenario and they would see something in those plots that just didn't quite make sense. So they'd schedule 30 minutes in the space. They would walk in. Typically they would animate through time backward and forth a couple times, and they go, oh, that's what it is. And they walk back out. So what was happening is they could see all these multivariate interactions. So most of the time they were mostly interested in how injecting or absorbing the reactive power in different parts of the topology was impacting these voltage profiles. It's a pretty hard thing to try to wrap your head around looking at a bunch of disconnected 2-dimensional plots. But in this space, you could see those interactions and see those interactions pretty clearly. So we're just giving them a way to look at their data in a different way. So again, I suspect there's this spectrum of multivariate complexity, and as we become more multivariate complex, that's where we're likely to see these inflection points of kind of improving value in terms of cognition and understanding, particularly if we can find interesting ways to leverage those extra degrees of freedom in our immersive spaces to embed those high dimensional spaces. There is a final dimension, and this one makes me a little bit more uncomfortable in terms of value, but time and time again, we've had groups come out of the space and report like, wow, we had all this really improved collaboration by being in there, and that's in terms of like stakeholder engagement and hypothesis generation and testing and planning and design. And oftentimes, they come in and make those reports to me, even with visualizations that I felt a little uncomfortable about. Uncomfortable in terms of I didn't necessarily see, as a visualization scientist, it wasn't clear to me that there was any perceptual or cognitive benefit for looking at those particular data in the space. And yet we still got these reports of kind of improved collaboration. And I don't think there's anything magic there. I would guess that it's just really a function of being a more active participant. That is to say, when you're in this space, you're kind of forced to stand up and move around and look, and you're really active in the conversation, much more active than say sitting, sitting at a conference table or around a PowerPoint presentation. So kind of on the tail end of this presentation, I did just want to say, we did integrate the original space almost 10 years ago. This fall, we are in an upgrade, and that's predominantly about replacing these projectors. So we started off with 6 Christie HD 6Ks, and this year we're replacing those with 6 304Ks. So these 304Ks provide a 4K 4K resolution. So our resolution is going to be moving from 10 megapixels up to 20 to 40, depending on what mode we run them in. And that mode is really about tracking. So with the 6Ks, we can run at 240 hertz. I'm sorry, with the 304Ks, we can run at 240 hertz. So originally we were kind of restricted to a single privileged view, but now with these higher refresh rates, we can actually track 2 stereoscopic views, or actually 4 monoscopic views simultaneously. So really excited about the collaboration opportunities that's going to open up. In closing, just to kind of circle back, I'm really seeing the value of immersive visualization kind of in 4 dimensions: improved spatial judgments, the ability to directly interact with your data. And I think both of those play into this notion of embodied cognition. Having those extra degree of freedoms that allow us to embed high dimensional space in new and different ways. And then finally, improved collaboration. A lot of what I've talked about today is documented in this chapter of the VR developer gems. So if you're interested in digging in, I'd encourage you to take a look, and then I'm certainly happy to answer any questions now or via email in the future.
Okay, that was very informative. I really appreciate you taking the time to share all of this. I'll open the floor to any questions if there are any.
Hey, way to plug that book, Kenny.
my pleasure, Bill.
Yeah. So I'm curious. Have you had any chance to try the multi-view prior to the installation you're doing this fall? I mean,
no, I have not used it. So basically, we'll be able to run that kind of in 2 modes. So we'll be able to run it in kind of the multi-view mode, where I can run 2 to 4, depending on if I'm doing stereoscopic or monoscopic. Right. Or I can just revert and just do a single view in 4K. So if I'm running 4 views in that space, that'll be kind of in a 2K per projector. And I'm hoping that works well, but I don't really know. I mean, I've been joking with people like, I think it's really going to open up a lot of opportunities, but that also means there are going to be like 4 images up there simultaneously for anybody not wearing the glasses. So I assume anybody not wearing the glasses is just going to walk in and throw up. Even if we don't like that multi-view angle, then we'll still have this kind of increased, opportunity to run in kind of 4K. So they're actually a 40 megapixel version of our space.
Well, yeah. So I guess I'm excited to hear what your opinion is after you'll have had it for a year. So.
Have you looked at the PC specs too to drive dual perspective like that?
Yeah, so it's intimidating. So we're going to be running this from 2 big servers. So we're actually going to run this. We'll have one server that's dedicated to multi-view, and then we'll have one server dedicated to 4K. And in both of those instances, we're going to run 24 display port cables from each one of those machines. So we're going to have 6 Pascal GPUs, 1 GPU dedicated to each projector, 4 outputs per projector. So we're running a lot of cable.
Yeah, I assume DisplayPort, right? And those fiber DisplayPort cables can be a little pricey.
For sure.
I'm just curious what GPUs you'll be using to drive those.
So this is going to be the RTX A6000.
More of a comment. I kind of really had to laugh about your musings about the engagement piece, where people get really excited to see a system and they just want to see something in 3D just because it's cool and because of the technology. And from the visualization scientist perspective, you're kind of like, well, what are we actually bringing? Is there anything we're adding from the data or anything like that? Are you learning something from this? And yeah, we've had to balance a little bit of both, but yeah, I do have a similar sentiment to that when people are just interested in having the engagement. But it's good. It's really opened the door a lot for people to start to explore the possibilities. And so we have had projects follow on that focus on that scientific visualization piece and the learning there. So
yeah, and that's why I more and more I've been trying to show kind of that example with the 3D bar charts, right? So that was something that was funded to come in, like we really want to see this adoption across the United States, and we want to see it in the CAAV. So we were able to do that, but able to very easily and kind of definitively show people like the questions you're asking are much better answered by looking at a simpler tact, right? So it's something that's been helpful as people come in and like because we're not kind of fixed to the CAAV. Like we've got a large 2D space as well, and then we support our HPC and a variety of other visualization modalities. And really, we're always just trying to help the domain scientists understand their data kind of in the best way. And it's always a little bit frustrating for me because we don't have those answers in terms of like when should we be using immersive visualization over something else. So it's kind of hard to push back on folks sometimes. But having those examples to say, hey, here's a pretty clear example of, depending on the question that you're trying to ask, maybe we should look at this in a different sort of way. Of course, that gets more difficult the more complicated the data is, and it's not always clear. And in fact, the example of the distribution system where we have, these lines, these geographical lines, was an instance where I pushed back initially, right? So the team, the power systems folks came in and said, oh, we really want to look at this power system in the CAAV. And, I shook my head and I said, you already have a good 2-dimensional projection of these data. It's probably just going to make it worse if I bring it in here. And we kind of went a couple rounds and, they were really insistent. They're like, no, we've got all these multivariate interactions that we don't think we're understanding well. And it was kind of through that dialogue that I realized, oh, like maybe there is enough complexity that somehow maybe there is some benefit to bringing this inside the immersive space.
okay, great. Thanks for the discussion. And let's see, further questions.
Yeah, I have one.
Sure.
Yeah. Hi, Kenny. Wonderful talk. I appreciated all the effort you put into this and the clear pictures you drew, no pun intended. My question to you is for your upgrade plans. You mentioned you're going with multi-view projectors. Did you give any consideration to LED displays?
We did. What I was really hoping to do, I don't know if you were able to tell from any of the pictures, but the design in that space, we've got kind of a wide, about 16 feet long, kind of rear projected glass. And then on the sides of that, the walls kind of cantilever out, right? So we really only got two surfaces that we're projecting on. And I was really interested in trying to take kind of micro tiles, like 120 hertz micro tiles, and kind of plaster, all those walls. So effectively kind of have some cantilevered projection. So if you did turn your body, you just have more of a field of view and a kind of a bigger working volume. We explored that a little bit, but it was in terms of both in terms of both our capital budget as well as our thermal budget, kind of those micro tiles weren't going to work out. So we kind of went a couple rounds and eventually just kind of came back to the more traditional projector.
Thank you.
Okay, we had a question come in, a comment and a question come in on the chat. It's a very nice talk. Are you thinking about remote collaboration with co-located collaboration?
So yeah, so it's something that we've done in the past, and we're pushing more and more on it. So one of the things that we've done is, particularly for more statistical visualization, is having somebody in the cave looking at a representation of the data and having that directly linked to somebody sitting at a more statistical interface, like an R Jupyter notebook. So when something is selected in the cave, that selection is represented in the notebook, or if something's selected in the notebook, that's represented back in the cave. And we've had some really great success with our scientists doing that, and we're trying to expand that, right? Really with the notion that different stakeholders necessarily may want different views into the data, right? So your statistician is probably most comfortable sitting inside that R notebook, while some of the other stakeholders may be better, better suited inside the cave, while we may have some program managers sitting in Washington that want to see this on a website as it's going on. So we're trying to facilitate those kind of collaborative interactions right now, and really excited about those types of kind of opportunities.
Okay, great. Any further questions? Okay, well, thanks again, and appreciate all the great questions and responses. So reminder, on the 23rd of September, our next talk is going to be about NSF funding opportunities. Then on the 28th of October, McDine will be giving a talk about some of their capabilities. And then on the 2nd of December, we're going to be having a panel discussion. And then as a follow-up, we'll be sending out a survey, just kind of get some feedback on this and see if there's any improvements we can make to the format, or even suggestions for people that might want to speak in the second semester of these talks in the spring. Okay.
Great. Well, thank you, John. Thank you, Frank. Thank you, everybody else, for your attention.
Yeah. Thanks. Good to see you.